Hi, this is Dr.G.Vikas. In this session, we'll discuss the problem on the proper cantilever beams. So, analyze the proper cantilever beam shown in the figure. Draw SFD and BMD. You can see the proper cantilever beam subjected to 50 kilonewton. The center, okay, and there is a prop at B and fixed and at fixed support at A. So, first of all, we need to check the DS value. DS is 4 minus 3. Total number of reactions minus equilibrium equation. So total number of reactions here is at A it is 3, at B it is 1. So 4, my total 4 minus 3, number of equilibrium equations 3. So 4 minus 3 1. So this structure is indeterminate structure, the indeterminate structure of 1 degree. So the next step, we need to remove the prop and calculate deflection, okay, and draw the bending moment diagram. We need to remove the prop P, and due to the load 50 kilonewton, what is the deflection delta 1 that we need to calculate. For that, we need to draw the bending moment diagram. So bending moment diagram you can see here in the figure, okay, WL 15 to 3. So we'll calculate YB1. The formula for YB1 is AX bar by E1 according to Morse second theorem. Now what is A here? Area of bending moment diagram. So half into base into height, triangle, no, therefore half into 3 into 50 into 3. Height is 50 into 3, okay. So 22.5. X bar is distance, central distance from B, because deflection is at B, okay. So 2 into 3 by 3 plus 3. So YB1 equal to, you will get it as 1125 by EI. In the next step, we need to remove the load and place the prop and calculate deflection due to prop delta 2, that is YB2. So YB2 equal to AX bar by EI. So area of bending moment, you can see the bending moment diagram here. RB into X is the height, base is 6. So area is RB half into RB into 6 into 6, and X bar is 4. So we'll get YB2 as 72 RB by EI. Equating YB1 and YB2, we'll get RB as 15.62 kilonewton. So we can draw the SFD and BFD. So BMD also we can draw. And how to find the point of contraflexure here? So equate the bending moment equation XX, which is between A and C. That equation is there, no, RBX minus W into X minus L by 2 equal to 0. So equate it to 0. Okay, then you will find X value. So X equal to 4.054. It is known as point of contraflexure, the point where bending moment is becoming 0. So in the same way, we can analyze the proper cantilever beam subjected to UDL. So find proper reaction, draw SFD, BMD, find slope, deflection at center, maximum deflection where shear force is becoming 0. So the same steps we need to follow here. First step is removing the prop, calculate the deflection due to load. In the second step, calculate, that is delta 1. In the second step, remove the prop and calculate the remove the load and calculate the deflection due to the prop, that is delta 2, okay, and then equate them. You will find P value, prop, okay. So in the next step, draw SFD. In the next step, draw BMD, okay, and in the BMD you will get a moment equation, okay. Now how to find the slope means using double integration method. What is the double integration method? So EI d square y by dx is equal to moment equation we need to do, okay. So this is the first step. Then integrating this, we will get EI dy by dx equal to so and so plus C1. This is equation 2. Now apply the boundary conditions. So what are the boundary conditions here? At A, that is at x equal to L, okay, x is taken from B here, okay. So at x equal to L, dy by dx equal to 0, and at B, that is at x equal to 0, dy by dx is maximum, okay. Applying this, using this boundary condition x equal to L, dy by dx equal to 0, we can find C1 value. Substituting this C1 value in equation 2, we can find the equation 3. We can get the equation 3, that is slope equation. Using the slope equation, we can find the theta B value, slope at B, okay. Slope at A is anyhow 0, slope at B we can find. Now deflection. Coming to deflection, again integrating the equation 3, we will get a constant C2. Use the boundary condition x equal to L, y equal to 0, okay, at A. So we can find C2 value. Substitute C2 value again in equation 4. We will get a deflection equation. And at B we need the deflection. So substitute x equal to 0. Then y equal to 0. Substituting x equal to 0 in equation 5. Okay, x equal to 0, y equal to 0. Substitute in equation 5. Then you will get a the deflection equation. Now wherever you need, you can find the deflection after getting deflection equation. Its center we need, but then substitute x equal to L by 2. You will get y at L by 2 minus as minus WL power 4 by 1 into 2a. Similarly, to find y max, partial derivative is EA dy by dx equal to so and so. That is equation number 6. We are partially derivating because we know that at a maximum deflection the dy by dx will become 0. Okay, so dy by dx equal to 0. Then we get, so after substituting dy by dx equal to 0, dy by dx equal to 0, we'll get x equal to 0.4221. Substituting x in equation 5, we'll get y max, that is 0.00545 by EA WL power 4. Okay, to find shear deflection where shear forces become 0, substitute x equal to 3L by 8. By substituting in equation 5, we get y equal to minus 525 WL power 4 by 9 to 8304 into EI. We can draw a shear force and bending moment diagram. So if you see the shear force diagram, at some point the shear force is becoming 0. How to find that value, x value? Equate shear force equation between A and B to 0. Then we'll get x value as 3L by 8. That means at x equal to 3L by 8, shear force is becoming 0 and bending moment will become a maximum. And after drawing bending moment diagram, you can find the point of contraflexure by equating bending moment equation to 0. We can find the point of contraflexure, x equal to 3L by 4, the point where bending moment is becoming 0. Now how to find out maximum bending moment value? Simply substitute x equal to 3L by 8. So okay, in the bending moment equation, so 9 by 128 WL square we get. So for proper cantilever beam subjected to UDL over the entire span, we are getting the RB as 3WL by 8. Okay, and then we can draw SFD BMD in this way. So as already discussed, to find the slope, first we have to take the bending moment equation and equate to the EI d square by dx square. Integrating when time we'll get a slope equation. After applying the boundary conditions, we'll get C1 value, and again integrating we'll get it, the deflection equation C2 value using another boundary condition. So in that way, after getting deflection equation and slope equation, we can find a theta b and yb, substituting x equal to 0 in the slope and deflection equations. So you can see the complete procedure here in detail. So y max, y shear force at 0 is calculated. Now let us discuss another problem on this propped cantilever beam subjected to point load and UDL, combination of loads. So find the reaction of propped cantilever beam as shown for the figure shown. Draw SFD and BMD. The first we need to calculate DS value. Total number of reactions 4 minus 3 equal to 1. Okay, a single degree indeterminate structure. In the step 2, we need to calculate the prop P reaction at RB. Okay, for this the first step is to calculate the deflection due to load by removing prop. Okay, so delta 1 equal to AX bar by EI. Here two loads are there, so separately we need to draw. First we have drawn bending moment diagram separately. For UDL we have drawn, you can see there W square by 2 and the W square by L, and it is for point load it is WL. Okay, separately we have drawn bending moment diagram and we have calculated A1 x1 bar plus A2 x2 bar by EI is equal to delta 1. So what is A1 area of that cuboid, parabola? So 1 by 3 into base into height 4 into L down 15 into 4 square by 2 160. Area 2, area of triangle, half into 20 into 6 into 6 to 360 meter square. X1 bar is 3 by 4 into 4, you can see the figure, plus 2 plus 3. Okay, from B we have to take because of deflection is at B. Okay, now x2 bar is the centroid distance of second figure, and then x2 bar equal to 2 by 3 into 6 plus 2. Okay, x1 bar, x2 bar we have calculated. Substitute all these values, we will get a delta 1 as 3800 by EA. In the next step, removing the loads, calculate delta 2 due to prop only. Okay, so here it is P into A. So area is a area of triangle, half into L into H, half into 9 into 9, P into A. Okay, so 40.5. X bar is L by 2 L by 3, 2 into 9 by 3 is equal to 6 meters. Okay, from X bar from B we need to take. In the next step, simply equate delta 1 and delta 2. You will find P value as 15.63 kilonewton. Then draw SFD and BMD. We know how to draw the shear force diagram and bending moment diagram. We need to take the sections between each spans. Okay. Now you can see the shear force diagram and find bending mode diagrams here.